We can offer a fully automated process from start to finish. What we're trying to do is leverage that background and that expertise in motorsports to bring it to any other industry. When a company comes to us, whatever they can do internally, unless they have quite a lot of experience on it, their costs are going to be, first of all, fixed. When you're doing a competition where all the cars are homologated, if you are not exact every single time that you do this test, then you're giving an unfair advantage to another team. We had a wind tunnel test on our rack, and the delta of that device was about 13.5% in the wind tunnel, and in our CFD simulations it was 12.8. So we're talking about very close margins.
All right. Ladies and gentlemen, another guest, another expert on the show today, talking about mastering CFD and wind tunnel testing for high-performance motorsports. Adrian, welcome to the show.
Hello, Joseph. Thank you for having me. It's a pleasure to be here.
Really cool. Give us a quick introduction, who you are and what you're working on at the moment, Adrian.
So my name is Adrian Villar. I'm an aerodynamicist. I am the managing director for VFluid Advanced Technologies. We are a small consultancy engineering company that we offer solutions to our clients on the fields of fluid dynamics and thermal development.
Really cool. How did you get started with VFluid in the first place? Because there's so many consultancies out there, especially in the field of CFD, but you have a special expertise, right? You're kind of on the experimental side, but also on the CFD side of things. So what is kind of the USP of VFluid in the first place, and how did you get started initially?
So my career started in Formula One. So I worked on a couple of teams for about 7 years. And then I joined Dyson Automotive, where I was the lead CFD engineer, handling everything related to the CFD methods. And by the end of the project, I was the head of the department for the aerodynamics department for the automotive side. And once Dyson decided to finish that project, I decided to start working as a consultant, and VFluid was born from that drive, really. So what we're trying to do is leverage that background and that expertise in motorsports to bring it to any other industry. And if you wonder why motorsports, it's mainly because motorsports, for me, it has a unique property compared to other industries, which is the fact that when you're developing a car in Formula One, or in Formula One or in motorsports in general, you are going to be benchmarked every single race, or every couple of weekends. Your product is going to be compared to every other competitor. So that forces you as a company and as a team to actually thrive and push the limits and always go for maximum efficiency, to improve your procedures and try to always be the best at what you do. And that's what we at VFluid are trying to bring to the rest of the industry.
Yeah, I like that. When we talk about AI, for example, there's always this discussion of like buying it off the shelf or like building the expertise in-house. Now, when it comes to CFD and consultancy, or being a consultancy, a CFD expert, what is kind of the benefit if you bring someone like you in-house, or like buying the expertise from externally?
First of all, like us in VFluid, we're not only about CFD, we're about everything related to fluid dynamics and thermal development, so from start to finish. But to answer your question, you can purchase a software in a commercial software like StarCCM or ANSYS Fluent. However, if you don't have the expertise to actually use the software, you don't know, you don't have you're not going to be sure that your results are going to be correct or actually representative of what the real world or what you're trying to simulate. And after that, it doesn't mean that it's going to be an efficient process. So what we take, for example, in-house, like we use StarCCM because we think it's a brilliant tool, but it allows us to basically automate to everything, to the rest of the procedures of development. So it's not about just using the CFD tool. It's about using the CFD tool in the correct way with the correct features of the tool, but also taking that tool and integrating it into the rest of the process and making it more efficient overall.
I see. What are some of the other advantages that people get when buying the expertise from you guys, or like getting the expertise from you guys? I mean, obviously there's this whole point of not having to buy engineers, or like, you know, having them fixed in the workplace. I don't know, maybe they have whole departments.
Yeah, of course. It will depend on every company because every client is different. And for us, we think we take every client as a unique opportunity. So we try to understand what their requirements are as a company when they're developing their product, and we try to help them in those requirements. So we, for example, as I was saying before, we can work with a company to develop a product from the beginning, from conceptual design to all the way until the final release of the product is done. And that means working throughout all the stages. So from CAD design, which can be surfacing, or CAD part design, and also that the way we implement that CAD, or we use that CAD, is we create the surfaces, for example, in a way that are as parametric as possible, so that that process of changing the surfaces is efficient and is quick, and when we use that output as an input for our CFD simulations, which can be as automated as possible as well. So that what we're trying to do is integrate all the different parts of the development, so that the process overall is as quick as possible. So that brings that improves the turnaround time, and lowers the overall costs of the process. So when a company comes to us, whatever they can do internally, unless they have quite a lot of experience on it, their costs are going to be, first of all, fixed, because they're going to have to hire someone, and then that person is going to have to gain experience, and that experience of what we can bring can take years, and overall costs that can be increasing over those years. So what we bring is those tools to this company, to our clients, so that they don't have to worry about having to set up new procedures, and all they get is results as quickly as possible, but also making sure that they are good results and that they will allow that product to be developed in a correct way, and in a timely manner. Because always, when you're developing a product, if you go over time, then that company is going to start losing money as well. So that's critical.
Yeah. With all your expertise, what have you identified, Adrian, was in terms of technical, business, but also operational bottlenecks that you guys removed because of your expertise, having seen so many different companies and motorsports teams, etc.? What are some of the, maybe let's rephrase it, the most common bottlenecks in the industry?
I think perhaps the CFD side of things is a bit of a bottleneck, because what I've seen in the past is a lot of companies tend to run simulations, and for example, in a single ride height, and they don't take into account, or they don't give the priority or the importance that it requires. If we're talking about a race car, a lot of the companies that we've worked in the past with, they are able to run in a single ride height and a single attitude of the car, and that's how they develop the car. So if you do that as a company, or when you're doing that to develop a race car, you're not going to take into account how the behavior of the car around a track is affecting the performance of the car. And in aerodynamics, you have to be able to take into account not only how the car is behaving on a straight line, but also how it's going through the corner, and depending on the type of corner, for example, because it's not the same if it's going through a slow speed corner or a high speed corner. So the behavior is different. The yaw conditions, the roll conditions are different. So this, what I've seen with our clients is that they've developed the car in straight line, for example, and there's no point. That's not going to give you a good idea of how the car is actually performing on the corners. where you actually get the most advantage in time per lap. So what we do, for example, we have we can offer a process where we don't only take we can run the same configuration at several ride heights and attitudes, so that we can perform an aero map, and that way we can understand the sensitivities of the car, and if we highlight any areas where there's an issue or a drop in performance, then then we can fix it in time. Because otherwise, if you have a car that you're developed on just a straight line condition, and then all of a sudden you go to the track, you manufacture the car, you go to the track, and the driver goes around the corner, it loses performance, or it drops in downforce, then the driver is just gonna slow down and not going to be as confident as he could be if the car was more uniform in terms of how it performs. So that's one of the things that we are able to do for our clients. So we take a single configuration, we automate it so that with a single click, you get a full aero map after a few hours of simulations, and then use that for data analytics. But the important thing is not just the fact that, because running a CFD simulation can be somewhat simple, the question is whether that simulation is actually correct. So we have a lot of experience doing this sort of simulations, and we have done a lot of wind tunnel testing as well, which is where we believe needs to be a balance. When you do aerodynamics, you have two main tools. One is your CFD simulations, and the other one is your wind tunnel testing. Mm-hmm. And wind tunnel testing can be expensive, but it is a requirement to make sure to validate your CFD tools. If your CFD tools are wrong, then there's no point on doing that. The other thing is that when doing a wind tunnel test can also be very wrong. There's a lot of variables that go into running a successful wind tunnel test. You have to take into account all the boundary conditions. You have to make sure that the car setup is correct, that the car geometry is correct, and so on. So that's where our expertise from experimental validation and CFD simulations come in and make an important feature for our clients. So that balance, it's where what we offer, basically.
That's pretty cool. Would you say you're also working with the FIA, because I've seen the logo on your website, also helps you? It's kind of an unfair advantage, let's call it like that, when it comes to you guys working in motorsport?
Yeah, so our work with the FIA, we're technical advisors when it comes to aerodynamics on the WEC series. WEC is basically GT3 and LMH. As part of that job, we also have to liaise with ACO and IMSA, so they are the counterparts from Le Mans and the United States, mm-hmm. Because some of their cars run in WEC and vice versa. And the job that we do is basically make sure that the regulations from WEC are in line with what the teams present when they come to the homologation process. So when we talk about homologation, is that this series have a set of rules that the amount of performance or the performance of the cars is homologated. So it has to be within a set of boundaries, to put it somehow. So engine performance can have a certain amount of output, and when it comes to aerodynamics, it has to be within a range of drag and lift coefficients. So what we do is make sure that every time we go to the tunnel with every team, the car that the teams bring are within the regulations, and also help the teams get to that point in the preparation phase. But while we're in the tunnel, we also need to make sure that the setup of the car is correct. And it's very important to highlight this, because when you're doing a competition where homologation, where all the cars are homologated, if you are not exact every single time that you do this test, then you're giving an unfair advantage to another team, for example. So, and when I talk about setup, I'm mainly talking about, for example, the ride height system that the cars have to fit to perform the test, because during the wind tunnel test they have to install a hydraulic system that allows the car to change ride heights as well as yaw and as well as roll. So basically, we do a full aero map of the car inside the wind tunnel test. So if when we're setting up the car, if the car is a 50-50 in terms of front ride height and rear ride height, and you make a mistake and you set one car to 52 instead of 50, then you're giving an advantage to that team, because the downforce level that you're measuring is going to be wrong. So we have to be very accurate and to be able to have a fair series, basically. And as part of that, our understanding on how wind tunnels work and how the aero maps are created has to be very much on point, because we work, for example, with the performance team from the FIA to actually make sure that the aero maps that we are using as part of the homologation are as representative as possible to what it's seen on track, and that level of the performance that we see on the cars is representative, so that the performance team can do a proper BOP or balance of performance for the cars prior to every race.
Super interesting. How does the approach differ in terms of the different vehicle segments, such as road cars, hypercars, race cars, and then F1?
Yeah, so that's an interesting question. As I said, like, every client is different and every client is unique for us. And when you're talking about different industries, it makes it even more important. So when you're taking a road car, for example, what you develop is the requirements of that road car. So when road cars, for example, drag is one of the main criteria of performance. So you want to make sure that your drag is as low as possible, mainly because drag is going to give you the amount of fuel consumption that you're going to get. But when it comes to cars, road cars, you need to make sure that they are safe as well to drive. So that means looking into crosswind conditions. And crosswind is different to yaw conditions that you see on a race car, for example, because when a race car goes around the track, it turns and the rear can move slightly, and that means that you are running in yaw. When you're in a road car, you can be driving on a straight line on a highway, and you can have wind coming at an angle, and that can provide something similar to yaw, but your road is in the same direction, so the behavior is slightly different. So you need to take that into account, so that to make sure that your crosswind sensitivities are as low as possible, so that the car is not sensible to any major crosswinds. Plus, the crosswinds that you study sometimes can be, 90 degrees of crosswind, which is not the same as the wind average crosswind. But you need to take into account all these parameters. But when you also have a road car, you need to make sure that you take into account aeroacoustics. Because you need the driver to be able to focus while it's driving, while he or she is driving for 6 or 7 hours. And if you have a lot of noise inside the cabin, then that can cause issues on the driver to be able to focus during that time. And depending on the car, depending on the type of road car, if it's a luxurious brand, they will want to avoid, for example, the driver from getting their hands dirty when they open the doors. So you have to look into soiling in order to be able to do that. Or when you're designing a road car and you're designing a sedan, for example, and you don't want to have a rear wiper, you have to take into account your soiling simulations to be able to avoid or make sure that the dust from when it's raining is not going to settle on your rear window. So every case is different in terms of what the requirements are. You might have also aero balance shift targets or ranges that you want to use to make sure that the car is stable in every condition and so on. On the other hand, when you go towards race cars or hypercars, your requirements shift slightly. So when you go to a hypercar, you have to consider aeroacoustics as well. But you also need to start taking into account the performance of the car around a corner, because you need to make sure that that car is stable in order to go at 300 kilometers an hour, both in crosswind, but also in a high-speed corner, for example. So those requirements vary depending on the type of car. When you go to Formula One all the way to the other end, then you don't care about soiling, you don't care about aeroacoustics. All you care is about performance, to make sure that that car is as fast as possible and drivable as possible around a track. So that's where that's the main difference when you're designing different types of cars. It's just the requirements for each one are different, and us as consultants, we have to make sure that we understand the requirements for each one of the types of products that we're developing, but also from the company, to understand not only the requirements but also the limitations.
I see. When it comes to the CFD automation bit, how much do you actually automate of the whole process, from meshing to processing to actually post-processing? Because I can imagine if you have different types of crosswinds from different angles, you probably just parameterize it, right, in the script.
Yeah, correct. So we can offer a fully automated process from start to finish. So we can have a parametric CAD model, surfacing model, that it's done to high standards, and that means that when it comes to CFD simulations, it's basically a fully sealed surface. Mm-hmm. And then that surface goes through a process that cleans it up to make sure that it's not going to give any issues when it comes to meshing. And then the process automatically meshes the surface and solves the simulation depending on whatever type of simulation we want to achieve. And then it automatically post-processes the simulation. When it comes to the requirements of how we perform that simulation, we can talk about using RAN simulations and also transient simulations. The use of both will depend on both the requirements and limitations of the client, but also on the stage of the development of said product. Mm-hmm. So as I was saying, like if you're doing a race car, and you're at the beginning of the stage of development, that race car, you might want to have larger changes of the geometry to understand where or to try to come to an agreement in terms of, or a convergence of, how the overall geometry of the car is going to be. So at the beginning, for example, if we're talking about, I don't know, a Le Mans car, you want to have design your splitter, and you might want to understand whether you want to have your maximum loading of this front splitter in the central portion of the front splitter or towards the outside. So you can start making parametric studies where you vary that loading from inboard to outboard and so on. And because there are large geometry changes, using RANs is perfectly good for that, or it will give high accuracy and good enough results for this type of simulations and type of understanding that we're doing, a type of study. And by using RANs, what you're doing is just increasing your throughput of simulations as much as you can. And also, it allows us to, for example, if we want to do full aero maps on some configurations or every configuration, we can do it at a low cost. So we are also able to leverage transient simulations. You can always have a balance between the two, or do full transient simulations if you are in the process of already having the final release of the product or the car in this example. The use of transient simulations, it can give you higher accuracy of your results, and also an understanding of of any transient behavior that you see on the car, which is also important. So it's a matter of having a good balance to make sure that your costs are not too elevated. Because when you're talking about, for example, you can have a transient simulation that will cost you, I don't know, it depending on the simulation, it can cost you $500, but you can also have a RAN simulation that will cost you $35, $40. So that difference is significant, so that if you can do as much as you can with RANs and then balance it or support it with your transient simulations, then you're going to have a good outcome as well from your project.
I see. What would you say was the most exciting project that you've worked on? If you could obviously talk about it, and maybe if you think about the less attractive projects, what are some of the things that are maybe hard, especially for CFD experts and experimentalists like yourself, when getting into a project? Some of the hard bits, if you know what I mean.
I think one of the toughest things from a new client, for example, when we start a new project, sometimes is the quality of the CAD. I mean, it's not something that it's a showstopper or anything like that, but sometimes it can be quite time consuming, and it makes it less efficient, to put it somehow. So like, for example, if you're working with an automotive company and they're already in the final stage of development, it's completely normal and understandable to get this sort of thing, but it's not something that it's a big issue, because we tend to run those simulations on the parts of the car, on the real parts of the car. So that means having a full chassis and all the intricate details of for example, the engine cabin or the motor cabin. So that it's not an issue, because there are tools that you can use to actually be able to run this without problems. I think the biggest issue, for example, we have a client that has been working with us since the beginning for over 4 years now. It's a small startup from the US, and they develop devices to reduce drag on trains. And it's been incredible working with them, because it's been quite a challenging project, especially at the beginning. We had to set up everything, all the automated tools for them. But the main thing was the CAD was basically taken from internet files. And basically at the beginning it was quite a struggle, because the files had overlapping surfaces everywhere and so on. So we had to we use these tools to actually get the RCFD simulations running, but it was quite inefficient. The mesh was taking too long and so on. So we basically just said, let's do the CAD from scratch. So we drew, based on those surfaces that we had, we drew the entire locomotive and cars and train cars from scratch. And all of a sudden, we saved, I don't know, 80% of the meshing time, or the pre-solve time, just by doing that. So it's a matter of adjusting and knowing what's more important. If it's a long-term project, it's completely worth it just doing that change in the CAD and taking that time, rather than using tools that every single time you make a change, for example, then it can take time for the mesh to run, for example. But it's funny, because with that client that we've done not only a lot of CFD simulations, but we've done some of the biggest CFD simulations we've ever done before. So we've ran simulations of nine wheel trains plus locomotive, and that was over 800 million cells for a RAN simulation. And so it's quite a heavy simulation to be able to run. And as part of the whole process, we've been able to do from A to finish, do loops of the entire development, because we started from concept design all the way to CFD simulations and wind tunnel testing to validate the simulations, and very proudly saying that the results from those wind tunnel tests were very much in line with every single simulation that we run. So the deltas were exactly the same, or not exactly the same, but we're talking about, for example, we had a wind tunnel test that had an auto rack, and the delta of that device was about 13.5% in the wind tunnel, and in our CFD simulations it was 12.8. So we're talking about very close margins of that delta. And as well, we had pressure taps in the wind tunnel model, and the deltas or the differences that we saw in the pressure field in those where we had the pressure taps were very close, just a minor difference in one of the areas. But so very happy with those results, and it gives us the confidence that our CFD simulations are working properly.
I think that's super interesting, Adrian, when it comes especially to the automation of all the CFD process. So I think we should probably have a deep dive on that. So we're going to cover that. So everybody who's interested in that, let me know in the comments, and we'll make sure that this session is going to happen. How can people reach out to you if they're interested in working with you, Adrian?
I think the two easiest ways to get in touch with us is through email or LinkedIn. You can find me on LinkedIn. My name is Adrian Villar Collazo. You can find the company called VFluid Advanced Technologies, or you can email us at info@vfluid.tech. Our website is vfluid.tech, so you can visit us and get a better understanding of what we do. And you can see some of our blogs from some older projects. There's a project with an old 911 that has had some attention. So yeah, just feel free to go in and reach out.
Awesome, Adrian. Thank you so much. And looking forward to the deep dive very soon.
Thank you very much, Joseph.